Okay, science time. Today we're gonna, first we're gonna look for a marker that actually functions, hopefully. Let me see if I can find a fully functional marker in this drawer of many things. Okay, this one's green. That might work okay. Let's write down the objective, which is describe and model the electromagnetic force. Describe and model the electromagnetic force. We are going to get into in the next lesson, we're going to get into fields themselves, fields as an idea of forces. In my opinion, it would probably be easier to understand both the magnetic and the electric portions of the electromagnetic force if we talked about the fields first, but we didn't, so it's too late. Let's talk about the about electricity. Electricity. Yeah, well, let's call it that. Let's call it electricity. Let's spell it right. Let's start over. Let's start the video over. We're having to spend the whole first, this is a real mess. I've spent the whole first 5 minutes looking for a marker. The marker is fine. I can't spell electricity. There we go. Electricity. Everyone else had already gotten it. Electricity. What's your favorite thing about electricity? Heat. Thanks. Tommy. The lights. Her likes the lights. What else? What else do you guys like about electricity? You like that you can get on TikTok? You like that you can look at your mom's Facebook? You like that you can use your blow dryer? Electricity is great, isn't it? Mm-hmm. Makes your life super easy. You like that you can toast your toast in the toaster and not have to toast it on a piece of fire. That would... The refrigerator, yeah, so you don't have to die of bloody diarrhea. These are all great things because of electricity. Electricity, which I still might have spelled wrong. And I don't know, this is not a fundamental division, but there are really two kinds of electricity that we talk about. We talk about the idea of static electricity, and we talk about the idea of current electricity. Your book primarily focuses on static electricity, but we'll talk about both a little bit. What is the root word of static? We had talked about this on Wednesday a little bit. What's the root word of this? Do you remember? No, okay. Does anyone remember? What was it? Someone said something. When you think of static, you probably think of, as I said on Wednesday, either it's like static on the television set, or static on the radio, or static hair, or maybe you think of the shuffling across the room and touching your brother on the nose and shocking him, or you think of the balloon sticking to the ceiling like you did in the lab. But static really, on a more fundamental linguistic level, static means to stay. So I could say, the grade point average in this room is static. And that does not mean that it's fuzzy hair or that it'll stick to the ceiling. It means that it stays generally the same over time. You see what I mean? I could say that the air temperature today is pretty static. That doesn't mean that the air is staticky and it's going to make your hair staticky. It means that it's staying the same relative over time. The word static means stay. So why do we use it for those other things? Why do we use it to mean stick the balloon to the wall or hair? It's because of static electricity. When you're talking about that kind of static, you are talking about static electricity. The charges that are staying. For instance, if you have, this is you. You have a ponytail. Of course you have a ponytail. You have some other hair too, but you have a ponytail. Someone said Tommy. I did not say Tommy. I mean, I just did, but someone else said Tommy. So anyway, this is Tommy. And just like, you know Tommy's always wearing that shirt that says her name straight up of it. Anyway, if your whole body is made of what? Yeah, that's what I'm getting. There's lots of other answers. Your body's made of cells, your body's made of water. There's lots of other things that are true, but we're talking right now about the atoms. So your whole body's made of little submicroscopic particles called atoms. And you know that on at least a basic level. You're aware of the existence of atoms. Each little tiny atom is made of some number of neutrons, some number of protons, both of which exist in the nucleus, and then some number of electrons that exist outside the nucleus. Nucleus, electrons. When someone else comes and rubs a balloon, red balloon, red balloon. Someone else comes and rubs a balloon on Tommy's hair. What's happening is, and it's more complicated than this on a physical level. In fact, interestingly, I wasn't aware of this until about less than a month ago, but this is one of the major unsolved problems in physics, is why does static electricity exist? We really don't fully understand. The current comprehension bases on, this is the part we don't understand, is the mechanics of this, but we do know that for some reason, the electrons that make up the atoms, that are part of the atoms that make up Tommy's hair or scalp or whatever, and remember the balloon is also made of atoms, which themselves are made of protons, neutrons, and electrons, but for some reason some of the electrons migrate, for lack of a better word, they migrate from the hair to the balloon, or vice versa. It doesn't really matter which way, but effectively the balloon ends up with either more or less electrons, which means that now it has a charge, what we sometimes call a static charge. Relative to the other atoms that are around it, it has a larger or smaller number of electrons. Do you see why it doesn't matter if it's larger or smaller? The important thing is that it's different from how it used to be. For instance, this is definitely not the way it is, but say the balloon has 12 protons. What's the charge of the proton? Uh-oh. What's the charge of the proton? Positive. It certainly does not. It probably has more than 12 trillion protons, but we'll say it has 12 protons just to make the math easy. And it starts out, it's neutral, and so it also has 12 electrons. What's the charge of the electron? Yeah. So they have the same charge, and so it is neutral. If we have 10 positive, look at this. 10 plus negative, 12 plus negative 12 equals 0. That's extremely simple math. It's not third grade math, but it is simple math. So what's happening is that some of the electrons in the balloon are going to the hair or vice versa. What I'm getting at is it doesn't matter because now when we do that rubbing, this is Garrett, one R and two T's? When Garrett rubs the balloon on Tommy's hair, whether the electrons are flowing from the hair to the balloon, giving it a negative charge, or from the balloon to the hair, giving it a positive charge, doesn't make any difference because now they both have a charge. And what is that charge? Well, sure, let's say here, and I'm going to show you in a second why it doesn't matter, but let's say the balloon is positive now and Tommy's head is negative. What's true of positive and negative charges? That's not true. Try again. Opposite charges. This is probably the most important thing from this whole lesson. Opposite charges do what? This was true of magnets too, and you got it really fast with magnets. I don't know why this is so hard. Opposite charges attract. Like charges do what? Repel. Go give me a balloon real quick and blow it up, please. Thank you, Tommy. Now, I put it on her face, but it's really her hair. The balloon has let's say a positive charge. The hair has, let's say, a negative charge. They're attracting. And you'll notice this when I bring the real Tommy and a real balloon up here, but her hair will be attracted to the balloon. And I don't know, it won't be super exciting because you're used to this happening. You're aware of the existence. You have an instinctual understanding, not maybe instinctual, but you have a learned or reasoned understanding of how static electricity works, and so it's not going to be shocking, but it is going to defy gravity. It literally will defy gravity. It's going to go against the force of gravity, pulling everything towards the center of the Earth. It'll pull it towards the balloon instead. There's obviously a stronger force than the weight of a hair. Admittedly, the weight of the hair is not very much, but a stronger force than the weight of the hair pulling it up toward the balloon. And what if I was wrong and instead the electrons have flowed to the balloon and now they have a negative charge and the hair has a positive charge? Well, it doesn't matter. It's the same effect, right? They're still going to attract. Whether the hair is positive and the balloon is negative, or the balloon is positive and the hair is negative, makes no difference. They're still going to attract. And then what if we did this? Who else wants to be in the picture? I don't know who that was. Miranda? Miranda. This is Miranda, and she has a balloon too. And she has rubbed a balloon. Pretend that balloon has been rubbed on Tommy's head. And we'll say again, the balloon is negative. Tommy's head gets even more of a positive charge. What would this balloon... This is Miranda. How will this balloon respond to Tommy's hair? The same thing. It'll attract Tommy's hair, just like the other balloon did. But now, if we get these two balloons close to each other... Can I have two balloons, please, Tommy? What if we get these two balloons together? They'll repel. They're going to repel. They have a static charge. And whether the electrons flow to or from an object depends on what the two objects are. Is this related to friction? Yeah, remember friction is the sliding past or the attempted sliding past of two objects. And what caused friction was that there were little micro welds that formed, little bonds, chemical bonds that form. And one thing that one thing that we have evidence for of friction in static electricity is that when those little bonds form, the little micro welds, remember when things are rubbing past each other, they form little micro bonds. When they form and then they break when they start sliding, some of the bonds are effectively stuck on the wrong side. Like the electrons that were on this thing, left hand, are now stuck to right hand, and so that gives it a static charge as well. When it's my hands, it doesn't really dissipate throughout my body because these things are connected. But when it's your feet on the carpet, the charge does build up in your feet, and then that carries through your whole body, and then when you touch your little brother, bzzzt, okay. Who doesn't mind being on the video? Oh, Josie. Whoa, that was really good. Okay, come over here, Josie. I don't know if your hair is long enough for this, Josie. Ready? Do you mind if I rub the balloon on your hair? It defieth gravity. Do you see that? Which way is gravity pulling her hair? Right as we speak, down. Yeah, towards the center of the earth. That's pretty sick, actually. I think that's cool. That's really neat. Yeah. Yeah, that's really good. Okay, hold on. I don't really want this to discharge, so I'm going to come over here. We got two balloons now. Is this one going to attract or repel her hair? Attract, still. It's the same thing, right? It doesn't matter whether it's positive or negative. It's still going to attract her hair. Okay, go sit down. I don't know how I'm going to display this, but I guess you'll just have to trust me that in the same way that when you get two same poles of a magnet together, you can feel. Do you see it? That probably discharged a little bit. Yeah. So now they repel. They have the same charge. Doesn't matter what the charge was. Thank you. Who else wants their head rubbed real quick? Good. Okay. Questions about static electricity real quick? You have questions about static electricity? No. What does, do you remember, what does the gravitational force depend on? What does the gravitational force depend on universally? No, what things does the gravitational force depend on? How do we make gravity stronger? Or how could we make... We're going to go... The mass of the objects is one thing. Remember, we had this equation. Let me do it in red. We had this equation for gravity. F sub g, the force of gravity, equals the masses of the two objects multiplied together divided by the distance between them squared times the universal gravitational constant. The force of the electromagnetic force is K, the universal electromagnetic constant, times the charges of the two objects multiplied together divided by the distance between them. Do you see a similarity between these two things? They're the same dang equation. It's just that one depends on mass, the other depends on charge, and then the constant is a different value. But they both depend on the distance between them squared. The closer objects are together, the more a gravitational, true, but also electromagnetic force of attraction can be between them if they're charged. The other difference is that there can be negative and positive charges. Remember, gravity is always attractive, but electromagnetism can be repulsive as well. Current electricity your book barely goes into, but current electricity is the flow of electrons. So where static electricity was electrons kind of staying, just like being on a thing or near a thing, current electricity is the flow, the movement of electrons from one location to another. We usually use, I'm going to erase all this, we usually use a circuit diagram to explain current electricity, and I'll just draw a very simple one. But we have a battery. This is the usual symbol for battery. We have some wires. This is a symbol for wires. And then we have some load. We'll put a light bulb there. We have some load. This is supposed to be the positive end and the negative end of the magnet. Of the battery. Electrons have a negative charge. In reality, they flow from the negative end of the magnet to the positive end, but we always show, confusingly, we always show the flow of electricity in a current as from positive end of battery to negative end. I don't know why, don't ask me. But as these electrons flow, the battery has some property, which we're not going to get into, but the battery causes what we call electric potential, or an electric difference. The electrons basically, and I'm going to use, this is going to be very elementary, but the electrons in reality are here and want to be here. Want to be. When I say want to be, they can't think, right? Electrons can't think. They don't have needs. The way the universe exists causes them to be that they go from one end to the other. Once again, we show it this way, but it's actually happening the other way. And as they pass through this load, which was a what? Do you remember I said? Light bulb. As they pass through the load, they power it. Basically, what happens in the light bulb, specifically a light bulb, is that there's this filament in it, and this is an incandescent light bulb. There's a filament in it, and the filament has a certain electronic resistance. And when the electrons try to pass through it, they have a harder time than going through the wire. And so they bump into the metal, and they cause the metal to get super hot, and it gets so hot that it glows. And that's how an incandescent light bulb works. But that's current electricity. Do you see the difference? In current electricity, it's flowing. In static electricity, it's staying. What's the similarity between them, though? Why are they both called electricity? No, they don't. They both have to do with what subatomic particle? Try again. Electrons. Then that word is related to electricity. Do you have questions about any of this? I think you do. Sage, what's yours?
So, when you said that the thing,
they don't catch on fire in that way, but really, the same thing that makes a fire glow is also what's making the filament of a light bulb glow. It's just that when particles get hot enough and they move fast enough, they emit called black body radiation. It's electromagnetic radiation. In fact, you just sitting there are emitting radio or microwaves because of your heat. But if it gets hot enough, that light frequency goes up into the visible spectrum, which we can see. So it's not on fire as such. And you could easily, if you had a light bulb, especially a high-powered light bulb that was incandescent, and you had some like dryer lint, especially if it was dryer lint soaked in like lighter fluid or gasoline, and you touched the light bulb to it, it would start on fire because it's hot enough. Other questions? Thank you. Yes, Tommy. It gets hotter to a certain point. Eventually, the longer you leave it on, this process does degrade the metal. The process of it being heated up, and then when you turn it off, cool down, and then heat it up again. That eventually will cause the light bulb to break in the incandescent light bulb. And in LED light bulbs like these, it works similarly. LEDs have a different, I don't remember what the symbol is, but LEDs have a different symbol, kind of like that maybe. And then they have a little, what's called a diode inside of them, and when that thing has electricity pass through it, it generates light, and mostly light. It doesn't get so hot that it lights up. It just causes light to, China has a little certain chemical substance in there that this frequency of electricity causes an emission of a certain frequency of light. Other questions? Like I say, your book primarily focuses on static electricity. Does this line up with what you saw in the lab? I wasn't here for your labs, but is this what you found in the lab as well? Okay. Bye. Bye, Lucas. Bye, Lucas.